Yeah. 46. I'm in 14.2. Is that one you wanted? Okay. So z equals 3x squared plus 4y squared minus axy. And they want to know values of a for which s is sloping upward when we move in the positive x direction at the point 1, 2. So sloping upward when we move in the positive x direction should set off light bulbs. What is this about? With respect to x, right? So that's going to, the slope of the surface would be like the rate of change in the direction of x. So we're going to do partial z with respect to x, and we get 6x minus 0, yeah, 0, and then minus ay. And if we want positive slope in the x direction, how do I have to force this to be? If I want the rate of change to be positive. If it's going to have increasing slope, then I got to force that to be positive, and I figure out what a has to be in that case. So it looks like minus ay is greater than 6x, and so then negative, and then so then ay has to be less than 6x, and a would be less than 6x over y. What does it say? Oh, but at the point, what? At the point 2, 1, so then a would have to be less than 1, 2?
Yeah. Yeah, 1, 2.
So as long as a is less than 3, that corresponds to that partial derivative being positive. Okay, part B. Oh, we got 3 parts here. Oh no, just 2. With the value of a from part A, if you move in the positive y direction from point 1, 2, does the surface slope up or down? Explain. So moving in the y direction is a matter of? Now we want the partial with respect to y. And we want to look at what happens when a is less than 3. So partial with respect to y is 8y minus ax. And so a is less than 3. Oh, at 1, 2. At 1, 2. So a is 1, 1, 2. So a times 2 minus 16 minus a. If a is less than 3, then what's always true about this? So a could, it's because 3, and then it's 2, 1, and then negative values will mean what about this? It's always going to be, would be greater than 0 for a less than 3. Do you see that? So like the biggest a could be, the biggest that you take away from 16 would be 3. Anything less that you take away from 16, it's just going to make this bigger and bigger. So for those values that make it slope upward in the x direction, it will always also slope upward in the y direction. Yeah, David. So that's just an old thing from like when you were doing when you learn inequality in algebra, like in junior high or freshman year. That like if negative 4 is greater than negative 8, which is a true statement, right? And we multiply both sides by negative 1. 4 would not be greater than 8. 4 is less than 8. So it's just a rule about solving inequalities. And that this is why. If negative 4 is greater than negative 8, then 4 has to be less than 8. Other questions? How about this one? Okay, 52.
Literally don't miss this class ever. If I have the phone, I'll just come in like a dream.
No, if you have the flu, stay home
Mhm.
and watch the video. If I don't post the video, email me.
Mhm. I didn't realize.
Yeah.
I was like, maybe he just maybe it was.
All right, so let's
In short, flu stayed away.
we're just gonna go with start with B. Let's bypass sketching the graph there. So what is the practical interpretation in terms of temperature of these two partial derivatives? Okay, so h sub x is partial derivative is, oh, I can barely read that. Is that all? So it's going to be 100 e to the negative, help me out, that's too small for me to see with my bad eyes.
Negative 0.1 t.
Negative 0.1?
Yeah, t.
That's all going to be constant with respect to x, right?
Yep.
And then this is going to be pi times cosine pi x for the partial derivative.
Yep.
And then we're going to do that at 0.2 t. So h of x at 0.2 t is 100 e to the minus 0.1 t times pi times cosine of 0.2 pi. And it says, what is the practical interpretation in terms of temperature of these two partial derivatives? Well, they're both the same, just with a different number plugged in. So we'll just do this one. So what is the practical explanation of this value of this rate of change of temperature? So this is what we worked on hard the last two classes. Who can tell me? Please, somebody. We worked long hours to interpret partial derivatives, remember? And then if you, I don't know if you realized, but as you were working through the homework, that meaningful interpretation that we worked on could have solved, just applying that could have solved probably 90% of the homework problems. Okay, it's really just, if you understand that interpretation that we practiced in so many different ways, you can use it to solve the problems. So what is that? Anyone want to give it a shot? Yeah, Max.
At the point 0.2, the value would increase by that whole thing per every t.
Okay, pretty close, pretty good. That's pretty good. So instead of per every t, that was a little, we could improve on that. So given what? Given a small change in t. And we call that, what's the small change in t? dt. Finish it. Given a small change in t?
The rate of change of the temperature.
Well, this is the rate of change. That's what we're defining. So given a small change in t, what is the h function? One minute. The conclusion is not about the rate. We have the rate, and we're interpreting the rate. So the conclusion is not about the rate.
Given the small change.
Given the small change in t, the resulting not temperature. Change in temperature, right? So rate of change can generate for us changes in the dependent variable. That's what it gives us. Rate of change gives us change in the dependent variable given some change in the independent variable. So the resulting change in what? Temperature, which would be like, I guess you could say dH. Or dz, if this is or capital T. So we call the whole thing capital T, then it would be dt. That'd be better. H is a function name, so you really shouldn't do dh, but d capital T. So if T is the quantity of temperature that we get from this function h, then the resulting change in temperature dt is, what is it equal to?
Is it that equation?
Yeah, either side, right? Both sides are the partial derivative. So you could write all of this, or you could write this thing,
Okay.
because they're both equal. Is that it? The change in temperature is the partial derivative? The resulting change in temperature is not the partial derivative. It's times the little change in temperature that you picked, or time, little change in time. This is the whole thing right here. So don't forget that. That's really important. And like I said, it solves this, understanding this and being able to apply this in different situations, like would solve like almost all the homework that you just got done.
So then just explain why each one would have the sign that it does.
Okay, so what is the sign of this? So this is an exponential is always positive. All this stuff is positive. So we got cosine of 0.2. The whole thing is positive.
Yeah.
So that's saying that what? As time increases, if this is positive, then what can we say about the temperature? It's increasing. And why does that make sense? Is it being heated up?
Yeah.
Oh, there you go.
And then it's,
So this partial derivative, this whole thing is positive. That's a positive value. Exponential functions are always positive for all t. So given a small change in t, if this is positive, then our dt is also positive, meaning that the temperature is increasing. And that makes sense if you're heating up the element. And what were you saying?
well, it says calculate h sub x of 0.2 comma t and h sub x of 0.8 comma t.
Mhm.
Do they want us actually plugging in 0.2 to the
Yeah, I guess I never did. Oh, I did that. So I did that here, right?
Okay, so and that's just the answer to have left in that.
Yeah, because this is now a function only of little t, right? And so that's what you have. You have a function only of time. At a particular length, is it like a particular radius or length on the bar?
Yeah.
I just can't read. Yeah, so now you're picking this particular point on the bar, and then you're saying as time goes by, what's the temperature? So it's just now it becomes a single variable function by fixing one of the.
Your fixed point is 0.2.
Yeah,
Okay.
you're fixing you're fixing the x at point 2, and now you have a function just of t at that point.
So both are going to be positive at 0.2 or 0.8 because they're both going to be.
Yeah, because 0.8 will just be 0.8 pi.
Yeah.
So they'll both be positive because
You're still heating up the bar.
still heating up the bar. No matter where you are on the bar, it's heating up, and so then
Yeah.
dt's will be positive. Okay, let's look at 14.3. We got a couple to look at.
Yeah. That one, 38.
38. So okay, so yeah, so this would be more difficult, but it's applying, like kind of putting everything we learned together. So let's so really what this is about like estimating the volume. Like if you had a tin can, it's like estimating the amount of volume of tin, right? If you increase the radius and the height a little bit, you're like creating some thickness to the sides, and so then that amount of dV would be like how much volume of tin makes up the can. Does that make sense? Let me show you. So it's like we have you have the cylinder, and so if you let the radius and the height increase. See that? So then it's like you're creating that change in volume that you would get would be like how much material of the can. Where did it go? Oh, there it is. Okay, it's on the desk. All right, so does that make sense? Do you see that? So dV is like this dV is like an estimate of volume of tin to form a tin can, right? It's not the volume on the inside. That's empty, right? It's just the change in volume due to a change in radius and change in height is like creating the thickness of the metal. And so then that dV from the thickness of the metal is like an estimate for how much metal. See that?
That makes sense. But how would you do it?
Yeah, we're about to. But I just wanted to get you like a vision of the problem. So dV is estimate of volume tin to form a tin can. Okay, so we're really asking for dV. And so dV is, the change in volume is, there's going to be a change in volume due to change in radius and due to change in height, right? So how do we get the change in volume due to the change in radius? It's the same thing all over again. Same thing. How do I get the change in volume due to change in radius? What do I need to do that?
Take the of radius.
What's that?
Their volume of radius.
What do you mean volume of radius?
So the equation is volume equals pi radius squared times height.
Okay.
So you would just take your function and find the rate of change.
Rate of change, partial derivative. Is that what you meant by? Okay. So when you said volume of radius, you meant the partial derivative. Yeah, David, is that what you're gonna say? Okay. So just calculate two v's and subtract. So yes, you could do that kind of like a v final minus v initial. So that's good, but it doesn't use calculus. It doesn't use that's a kind of another way to do it, and it in fact gives you like an exact result, but doesn't use any calculus. So if we're going to use calculus, it's a matter of dv is a result of a change in radius and a change in height. So the resulting a dv from the change in radius, we need, as Lucas said, the partial of volume with respect to radius. And then given any change in radius times that partial derivative gives us the change in volume. Same, a broken record, right? Broken record. But that's not the only contribution to the change in volume. What else contributes to the change in volume?
Change in height.
Change in height. And how do I get the change in volume from the change in height? I need the partial with respect to h times dh. And what will I do to get the whole change in volume? Add them together. So that's familiar. It's just you had to have a really good understanding to come up with that. And then, so that was a little bit of a stretch, right? This is a stretching problem. It's good. So where are these partial derivatives going to come from? A couple of you said it.
2 pi r squared.
Not 2 pi r squared.
But just pi r squared.
Pi r squared, not pi squared. Pi r squared h is where we're going to get these partial derivatives. So partial with respect to r is 2 pi r h times dr plus pi r squared is the partial derivative with respect to h times dh. Okay, so now we just did it give us values here? Yeah. So the radius is 50. So 50, go there. And the height is 100. What else? The height and the radius are both increased by 1 centimeter. Okay, so now there's a little thing to think about here. So the height,
dr and dh both
change
equal
in
one.
volume.
They're both just one.
Yeah, so they're both just 1. Now, so that's kind of different than what I was talking about. It's a little bit different than what I was talking about. If we were saying the thickness of the metal was 1 centimeter, and we wanted to get the estimate for the volume of tin, this wouldn't be right. Who knows why? There's a slight change we'd have to make. If instead of saying that the change in radius and the change of height was 1 centimeter, if I said, hey, I want the thickness of this can to be 1 centimeter, and I want to know what's the approximate volume of the tin, then this is not right. Why not?
Does that include all of the volume?
Not quite. So what's... Anyone see what's happening here? It's this right here. Why would that, if I wanted to make the thickness of the metal everywhere 1 centimeter, what's wrong with this right here? What's my DH then?
It should be 2DH because there's top and bottom.
Yeah, David, what were you going to say? That's right.
So I was going to say that since you only extended it by 1 centimeter, like top and
Mm-hmm.
you would only get like 0.5 inch, right?
Top and bottom. The radius is okay because 1 centimeter in radius, that means the radius goes all the way around. But the problem is here. This only increases the thickness height-wise of 1 centimeter. That gets me either 1 centimeter on the top or the bottom, but not both. So I need to include? No, I just need the total thickness of height to be 2. Right, I need a centimeter up here and a centimeter down here. That means DH would be 2. So that would be the case where the question asked, what's the approximate amount of metal for a tin can with thickness 1 centimeter? You need your DH to be 2 because you'd have a centimeter up there of thickness and a centimeter down here, meaning a total DH of 2. But the way they worded it, all they said was the radius changes by 1, height changes by 1, so you would do this. Okay, questions on this one? Doesn't make sense. All right, what else I want to look at? That was 38.
42.
42 and 14.3. Okay, so you can help me with, I can read about 75% of this. So T is f of x comma t, is that right?
Yeah.
And they're giving us the temperature, they're giving us a person standing 3 meters, the heater 5 minutes after, so they're giving you 3, 5, and they're giving us that value?
Yeah, they say it's 1.2 degrees Celsius per minute.
Well, they're saying it increases.
Oh.
That's the time increases.
Yeah, so that's a rate of change. Do they give us this actual value of F3 and 5? This is where you're standing at this amount of time.
No.
So they don't, okay, so we just have to use this, right? In terms of the starting temperature.
Yeah.
And then if you're going to, the temperature increasing 1.2 centimeters per minute. So what value are they giving you there? 1.2 centimeters per minute. How can we symbolize that in this problem? What is that?
The rate of change.
Rate of change of, so it's a partial derivative of f with respect to t. And is that at 3.5 at that point?
Yeah.
So by giving you the 1.2 centimeters per minute at 3 minutes, 5, whatever, 5 minutes and 3 meters away, they're giving you the partial derivative with respect to t. What else do they give you? As the person walks from the heater, the temperature decreases by 2.
3 degrees Celsius per meter.
What are they giving you there? Is it right? Is it 2 degrees Celsius per meter?
Yeah,
Not quite.
not as time is constant.
But what happens to the temperature?
Oh, it's negative 2 degrees.
So the rate of change is negative, and how can we symbolize that? What are they giving us there?
F sub x.
F sub x of
3.5.
So are you ready? Here it comes again, right? Can feel it coming? They're going to ask for some change in temperature, right? And how are we going to get change in temperature?
Multiply that, the f sub t or f sub x times the dx or dt.
Good. All right, yeah. So we can use this by multiplying it by a little change in time, and it'll give us the resulting change in temperature. And we can use this one. We can multiply this one by a little change in distance. It'll give us the resulting change in temperature also. So as the person walks away from the heater, oh, we already got that. Estimate how much cooler or warmer it would be 2.5 meters from the heater. So what does that imply? 2.5 meters from the heater. Got closer. So what does that imply? 2.5 meters from the heater implies what? How much change?
0.6.
Negative 0.5, right? And how do we symbolize that change? That's a how do we symbolize that? Right? So if we go from 3 to 2.5 meters, that's negative 0.5. And how do we symbolize it? That's our change in x. That's a change in x, right? X started at 3. Now it's 2.5, so the change in x is negative 0.5. What else? Is there also a change in time? What's the change in time? After 6 minutes. So 6 minutes means we went from 5 to 6 minutes. Therefore, 1 equals dt. See that? And what are we trying to find? We're trying to find the resulting change. So let's start with this. dt is and actually this is what it asked for, right? Because it asked for how much cooler or warmer it would be, right? This is how much cooler or warmer it would be, the change in temperature. Okay, hopefully by now everyone could write down how to do that. This is, again, broken record. This is what we did over and over again Thursday and over again in your homework. How do you get the change in temperature then? Brandon, do you know?
It's going to be the rate change times. So negative 2 times dx plus
Negative 2 times, and what's dx?
negative 0.5
Negative 0.5. Okay,
plus 1 times 1.2.
good. We matched them up correctly? Yeah. And so that is what, 2.2? What's the units on that? 2.2 what? It's a change in temperature. So if this amount of time goes by and you walk, that's a slow walk, right? To walk half a meter in a minute. Okay. Must not be very busy. Okay. The temperature will increase approximately 2.2 degrees centigrade if you walk towards the heater this far in a minute. Okay, did that? So then, Lena, you had a couple from the first section. Any questions on 14.2 or 14.3? Let's just do that one.
Yeah, could you do either 13 or 14 from 14.2?
I'll take a look.
Or wait. No.
All right, so we'll start with 14.1, 34. Okay, so this one. So they gave us this picture. See if I can reproduce it here. So these look like linear changes like this, and then okay. So it looks like kind of y is increasing linearly, but x is kind of increasing like by some polynomial or exponential function as you go in the negative x direction. So 3, 2. So this point is the point 3, 2, and then 1, 2. Okay, and so it's looking at both partials with respect to x and y and 0 in those 2 points. Okay, so what's bigger, the partial with respect to what? Let's do y first. Partial with respect to y at 3 or at 1? So this is at x equals 3 or at x equals 1. Which is bigger, the partial with respect to y at 3 or 1? At 1, right? This is a steeper line in the direction of y than this is. Okay, what about x? So the partial, what can you say about both these partials with respect to x, first of all? They're positive? Now changing their mind, negative or positive? Negative, right? As x increases, what happens to z? Decreases, going down, right? So you're going down. As x increases, z decreases in both cases. So these are negative. So these two partial with respect to y are both positive, but the partial with respect to x are both negative. Do you see that, Lena? So let's start with the biggest negative. What's going to be the biggest negative rate of change? Or the lowest value of all these? Partial with respect to x at 1, 2 will be the biggest negative. Do you see that? Because if x increases, z goes down the most. Compared to here, if x increases, z goes down just a little. So then the next one would be that one, still negative. And then what about the partial with respect to y? Positive or negative? So now y increases this way. Does z go up or down? And y increases this way. My picture. This one goes up slightly. This one goes up more, right? So these will be positive. So now 0 comes next then. Because these partial derivatives are positive. So the lower positive one is f at 3, 2 or 1, 2?
3, 2.
Do you see that? And then the biggest one of all is going to be with respect to y at 1, 2. That's a really nice question. Does it make sense now? So your partial with respect to x, they're both negative. This is the larger negative here because z changes more rapidly downward than z going downward here. So that's your biggest negative. Then this also is negative. Both the partial with respect to y are positive, the biggest positive being this one, because for a change in y, you have more of an upward of z compared to this one. So this is the lower positive, and this is the greatest positive. So yeah, you're looking at the change in z for a change in whatever, x or y. I'm gonna... Any questions on that example? Yeah, Max?
Can you explain 0 1
Well, your two x partials are negative and your two y partials are positive. So 0 has sandwich in between them.
Because I was just looking at it, and then at 0, it's just like here and here.
So 0 would be if you go in some direction and z doesn't change. And so negative will be less than that, and then positive will be greater than that. Does that answer it?
Yeah.
Other questions? Okay, what did you request?
14.2, either 13 or 14, just one of them.
14.2.
Maybe 14.
Oh, is this algebra? All right. You picked one? Which one did you pick?
Actually, let's do 13.
13, great. And can you read it to me? Too many small characters.
Yeah, so it's the partial derivative of x of x e to the square root of x.
X, e to the square root of x?
X, Y.
X times y.
Good, okay. So, what's the overall structure of this? That will determine the overall rule that we'll use. So what is the overall structure? Jake? What is this, like something to a power? Is it a product? Is it a quotient?
I would initially say that it's a product.
It is, because it's a product of x and another function of x.
Yeah.
So if the whole thing, its structure overall is a product, then what rule will we use for the derivative?
The
Product rule, right? So the overall structure determines like the overall rule. Now within the overall rule of the product rule, we may have other rules, but the big picture will be product rule. Does that help?
Yeah.
So do the first, or so the rate change of the first times the second plus the first times the rate of change of this. Now the rate of change of this, what is that?
That is the power law.
That's the
Or the
e, right? E, so the derivative of e to the something is e to the something, but then by the chain rule, times the derivative of this. Derivative of that is 1 over 2 square root of that, but times by the chain rule again, times the derivative of that, which is, with respect to x, y. So let's simplify it a little bit. E to the square root of xy plus b xy e to the radical xy all over 2 radical xy. And if maybe in the back of the book, did they have this? That whole thing is also just radical xy on the top. Maybe they simplified that too.
I think it's like 1 plus radical.
Oh, and then they factored out. Did they make this?
Over 2.
Yeah. So then this whole thing right here is the same as square root of xy on the top. It's kind of like 2 over square root of 2 is just equal to square root of 2. And then you're saying they factored out the e to the xy, so it would be e to the xy, square root, times 1 plus
Square root of xy.
square root of xy over 2. There it is. That's the square root of xy, that's the 2, factored out. E. Does that answer it? Yeah, so this is like, so within the product rule you have a chain rule, and it's like a double chain rule, right? So you gotta be really careful through there. Okay, last one. What was the last one? 34?
Yeah, there you go.
We did? Oh, but from 14, you requested 34 from 14.1. You want that one still? Unless, no. No, 30. Oh, right. So we did that. Oh, 14.46, sorry.
I think we did that one.
And we did that too. Okay, so did we cover everything? Okay, very good. Here we go. Okay, so here's a good kind of review exercise that leads us into the next concept. So we'll work this through together kind of quickly as a class, but it's kind of all review until we get down to the bottom, and then at the bottom kind of takes us into the next concept, okay? So the rate of change of f, so this is the 0.22. This is the contour plot for the function f. And how do those work? Remember, if you stay on a blue line, what happens if you stay on a blue line? Same output of the function, right? Same z value. So what kind of surface is this? Is this? Yeah, go ahead.
Can you I don't really understand like how to read those contour map things. How do you read them? Like from right to left, or like following the path?
So
like if they give you a point and it's with a z value,
And they ask
they
you
ask
for FX.
Yeah. So they ask you if fx is increasing or decreasing. How do you read that?
So let's do it. So I'm just going to make
I think we
something up
had
here.
some of those at home.
So
I still kind of don't understand it, but I still understand it. It's there, but all there. It's just
it's hard because they're getting so close together. Oh, he'll do it this way. Okay, this is easier. Okay, so this is 10. And then 0. And then -10.
Okay, so it's going down by -5.
so in the y direction.
In the y direction.
So then that would be,
-15.
this is -10 right here, right?
Yeah.
So that would be what?
-20.
That'd be -20. And then is that the next, is that 2 over? That would be?
-30.
-30 goes through, x equals 3. Okay, so what is just f of, so what's f of 2, 2?
-25.
So, yeah, what line are we on?
-25,
-15, right? This one, this is -20 here. And this is -10 here.
Okay.
Oh, okay. Yeah,
So you're looking top down.
Better?
Onto the
yeah.
So f of 2, 2 is approximately -15. Is that better? Does that kind of answer it?
So I get that, but then when they say like f sub x of 2, 2.
Yeah, let's do it, because that's part of this is to estimate the value of that. Yeah, Kyle.
I can tell the lines are going negative, like it's going -20 and negative.
I made it up. So I just assigned z values to this. So without those assignments that I made, it could have been increasing this way. And it could have been 100, 200, 300, 400. You just don't know unless you're given some values.
Okay.
Once you're given some values, then you can piece it together like you just did.
Okay.
But yeah, you have to be given yeah, some kind of scale, some kind of z values for at least a couple lines, and then you can pick up on the pattern. Okay, so that was just a warm-up for the actual value of the function. Now what about, this says what we want to represent the rate of change of f in the x direction at 2, 2. We want to represent that and estimate it. So how would we represent it? What would I write?
We do f sub x of 2, 2.
What's f sub x of 2, 2? Evan, you agree with that? The rate of change of f in the x direction.
Yep.
What's that called? Yeah, so we could say df dx like that. And what is that? What is that called? The rate of change in the x direction, or how do you find it? Partial derivative, right? Partial derivative. Partial derivatives give rate of change in either the x or the y direction, right? They give the rate of change, and the rate of change is this thing we've been working on for a week now, right? So this applying that. Okay, cool. So now we want to estimate that. So this is really the key to estimating that, right? So we want to estimate We want to get close to 2, 2. We want to get a change in z and a corresponding change in x, and then we can set up the ratio, and that'll be an estimate for the rate of change. So this notation kind of represents the calculation, right? The mathematics. It's a quotient, right? It's a quotient. So, well, so it's whatever you. This might be a little bit hard. Let me zoom in on it a little bit, and we'll figure it out. That's going to make life easier. So, but it's going to be kind of blinky. All right, so where's 2, 1, 2, 3, 4, 5. All right, so so you're basically looking at like how much change in z is that? So those are changes in z of 10. Negative 10 or positive 10 going in the positive x direction. So yeah, so your change in z is negative 10. I'm really surprised it still writes. For a change of x of what? So looking at your scale, so here's 1. It's as straight as I could draw it. And then here's 2. So what fraction of 1 is that change in x right there? A quarter? About a quarter. Is that? So for a change in x of 0.25, z is going down 10 in this vicinity where x is 2. Does that help? So now we can, from these two, from the change in output per change in input, we can get an estimate for the change in. So what would the estimate be? How would we calculate it?
So you do negative 10.
Negative 10?
Over 0.25.
Good.
So is it negative 0.25?
Nope. Positive. Because yeah, we're going that way, that's positive, and then z goes down. Is that 40? Negative 40? That's the rate of change.
Do you always want to just do one z value to the left and one z value to the right? Or can you try to do
What I did was I went one line in z. If it's easier, you could pick your constant thing to be the x, and then eyeball how much z changes. It doesn't matter. It's because you just need a ratio, right? So in this particular case, it was easier just to go over one line of z, and we knew that was negative 10, and then eyeball what the x was. But if you had if I gave you a grid, Cutter, if I gave you a grid of every 0.2, you could go over x of 0.2 and then eyeball the z, and then
Yeah.
Either way. Questions on number 1? Does it make sense? How I estimated that rate of change? Yeah, Max. I looked at how far. See this. Maybe it should have been 0.2 or something, but this is a dx of 1. Do you see that? So then it was this. It was from there to there, and I just was eyeballing what fraction of 1 that was. Maybe because it said 0.2 also. But it's estimating, so both would be correct. But 0.5 would not be correct, or 0.1 would not be correct. So it's somewhere a quarter of the way of a whole 1.
So you're just estimating the distance between the contours then? Each line?
Yeah, because I picked my dz to be the distance of only because I picked the distance. I picked one contour to be my dz. If I picked 2 contours to be my dz, then I would use that, right? So if I had picked 2 contours, oh, wait a sec, this isn't right.
Well, if you did
Why isn't this right?
Wouldn't the change in z be negative?
Yeah, it's negative 5, not negative 10. Negative 10 is 2 lines. We went over 1 line. So this should be negative 5. Yeah, we went over one line, and that was a change of x of about a quarter. So instead, this should be. So that was your question that triggered that, Kyle. Good job. So if we had gone two truly true lines over, that would be a change of z of negative 10. And then yes, the dx would be now 0.5, and we get the same estimate. It doesn't make sense. In the back. Colin, Lena, Sebastian, we good? Okay, now we have the estimated rate of change. So how much will z change if x changes by negative 0.4? Let's write it exactly. So I'm going to write something that will give me the exact amount of change of z if x changes by negative 0.4. What would I write? David. Yeah, tell me what to write. Good, that's right. So I want an exact, this is an estimate. So I want to write something that gives me this change in z exactly. You're trailing off. I'm not sure if you're thinking or if you're still telling me what to write. Right? I can't quite hear you, David. Sorry. No, because we're using the partial derivative at 2, We're not using the partial derivative at a different place. So I want to represent the change in z for this change in x. Is this what it is? No. What else do I need? Times negative 0.4. Okay, what about if I change x by 0.02?
Same thing.
It's going to be the partial times. Didn't leave enough room. I thought I did, but I didn't leave enough room. Okay? Yeah, David.
So negative 20 was an estimate of rate of change.
Yeah. Right. Yep. So this represents the exact rate of change, the exact value of the rate of change at 2. We estimated it by like eyeballing numbers off the graph. Hold on a sec. He's still talking. So yeah, these wavy bars mean approximately. So as soon as we start eyeballing numbers off the graph, it's not exact anymore. But this symbol means exactly the partial derivative at 2. But we're just getting an estimate by like eyeballing. So that's what the wavy equals it means. So if I'm asking for exact, then you have to use this notation. If I'm asking for an actual value of an estimate, then you can plug the negative 20 into it and do the multiplication. All right, so yeah, for all of these then, it's just going to be the partial of x at 2 times the change in x. Same thing, right? Same thing. So notice what is going to be if we let x change by 1. So this is the kind of the big important point here. If I let x change by 1, how much will dz change by? So letting x change by 1, the resulting change in z you get is the same as what? The partial derivative. Do you see that? And that makes sense because the partial derivative is per unit change, right? So it's like a per unit change. So that's going to come in later. But if I change by 1, when I multiply by 1, I'm just going to get the change in z is just going to be the partial derivative of x. So just file that away for a second. Okay, how much change in z if y changes by 0.01? So everyone write an expression. Write an expression. How much will z change if y changes by 0.01? What expression would you write to get that? Tyler, yeah.
Partial derivative with respect to y times
Times what?
times
Yep, and what's the change of y? What's that?
or 0.01.
Yeah, so yeah, dy or 0.01. That's right. Either one. Everyone get it? Okay, now, how much does z change if x changes by negative 0.04 and y changes by 0.1? Everyone write down that. How much does z change if? An exact expression for the change of z if x changes by negative 0.04 and y changes by 0.01. Colin, can you tell me that one?
Sorry, I didn't catch that.
Number 4. So how much does z change if two things happen? If x changes by negative 0.04 and y changes by 0.01.
Sorry, I got nothing. I'm sorry, I zoned out.
Okay, no problem. No problem. Brandon, you want to try?
Oh, yeah, so it would be f partial derivative 2 of x
Okay,
times the negative 0.04,
good.
and then the plus the partial derivative at y of 2 times 0.01.
You got it, Phil? All right, so now notice something. So now here's where we're going to kind of advance the conversation. Notice what is the ratio of the change in x to the change in y there? So notice that, do you notice that ratio is like a negative 4 to 1 change in x to change in y? Do you see that? Okay, so let's draw that up here. I'm going to draw that. It's kind of like I'm saying 2, so we're going to do negative point, we're going to go this far in x and then like up a little bit in y. Do you see that? So now there's like this new direction that's associated with these changes taken together, right? For every unit, for every unit up you go 1, you're going negative 4 to you're going 4 to the left or negative 4. Okay. So for that ratio, I want to know what changes in x and y taken together maintain that direction, that red direction, but then result in an overall change in the xy plane of 1. What would that be? So I want, right, do you see that? So what would that be?
Negative 4, 1 divided by square root of 5. Or negative 4, what is square root of 5? Oh wait, that was square root of 17. Not 5.
So I want to maintain this proportion of changes of x and y, but then I want that red vector to be magnitude 1.
Are we using the negative 4 and 1?
Yeah, I'm going to maintain, this is the negative 4, 1, right? This is the negative 4, 1 ratio.
So negative 4
Negative 4.
square root of 17.
I want it to be a unit vector, so? Everybody see that? So now that maintains this same proportion of changes of x and y that I asked in number 4, but then I'm going to go like a distance of 1 in the xy plane. Do you see that? My change according to both, when I change both of those together like that, my change will be a change of 1. So now what's the resulting change in z? No, do the math. Do the math. What is it? How do I get change in Z for combined changes, right?
Yeah.
Same thing I did here, right? So what will it be?
Oh.
Add what? You say Adam. Add what?
Like the x and
Times what?
times negative 4 over
Okay.
plus
Yeah, Kyle.
I'm sorry, but where is the square root of 17 coming from again? I know you did that.
So I wanted to have this proportion of changes in X and Y, but I only wanted to go a distance of 1.
So you just did Pythagorean theorem and then divided.
Magnitude, unitizing, right? Unitizing the vector.
You got the value because you did the Pythagorean theorem.
Yeah, you remember the magnitude? You remember?
Yeah, I remember magnitude. I just want.
Square root of the sum of the squares. That does.
Yeah.
It comes from the Pythagorean theorem.
Okay.
It comes from the Pythagorean theorem. Yeah. Okay, so now look. Remember when I said what was the deal? Oh, jeez. What was the deal here? When you make a change of 1, what is your dz? The same as? Which is? What is the partial derivative giving us? Rate of change, right? When you make your change of 1 and you calculate the change in z for a change of independent of 1, the resulting value of dz is the rate of change, right? Because you're multiplying that times dx to get dz, but dx is 1. So therefore, this is what kind of number? Remember, what's the distance we went? 1. Therefore, this dz is also one more time. When we chose a change of x of 1, what did we get for dz? The rate of change. It's that's the one case where the change in z you get is the same as the rate of change. Didn't we just go a distance of 1?
Yes.
Therefore, this dz is the same as the rate of change. When you take a combination of changes of x and y in this proportion, 1 to negative 4. So this is the rate of change in the direction of what? Negative 4, 1. Did you catch it? Doesn't make sense. When you go a distance of 1, like we did up here, the dz turns out to be the same as the rate of change. Well, we just did that. We just went a distance of 1 by forcing these changes in x and y to have a magnitude of 1. Therefore, the dz that we got is also the rate of change in that red direction when your proportion is negative 4 to 1. Cutter's got it. Chandler's got it. So what we just did is we just opened up the possibility for not only the rate of change in the x direction, and then not only the rate of change in the y direction, but the rate of change in any direction. Combinations of changes of x and y. So we just opened up the fact that there's really an infinite number of rates of change from a point. So notice this looks a lot like what vector operation? Multiply, multiply, and add. That's dot product, right? So what would it be the dot product of? Dot product of? What's that, Lena? fx and? So x components times plus y components. So it should be fx comma fy and negative 4 vertical 17. So this dot product This is what? This is a unit. This is not a unit. Sorry, not a unit vector. This is a vector of the partial derivatives. This is a vector. What kind of vector is this? Unit vector that represents some proportion of changes of x and y as a unit vector, right? Which that proportion of changes of x and y gives us some direction. In this case, it was the direction of -4 in x to 1 in y. This gives us the rate of change, then, in that direction. A rate of change associated with a combination of a change in x and a change in y together. This is called the directional derivative. So capital D for derivative in the direction of so right, I'm going to erase above, but you write below, okay? I'm going to erase above, but you can write it below. So this is the unit vector in the direction that we want to calculate the rate of change. This is the vector of partial derivatives, which is called the gradient vector. And you use this upside down triangle. It's a del operator. And this is called the directional derivative. So the derivative in the direction of u of the function f. So before we keep talking about this, any questions so far? Does it make sense?
Oh, you said the gradient vector was del f, right?
Del f, right? And this is like a vector. So like when you see it in a text, it might be bold, but you can't write bold, so you put the vector over it just like you would put the vector arrow over a vector.
And that is the vector given by the
It's a vector made up of the partial derivatives. That's right. And then this vector is our unit vector, indicating the direction that we want the rate of change in. Okay, so let's work on this. Any questions?
I just realized I'm writing colors.
So here's that same deal. Still got the pen on. Here's that same function. Oh, I should have asked. What is this function? So do the lines indicate a paraboloid, Colin? So you said it looks like a paraboloid. Do these lines indicate a paraboloid? And if so, why? The contour lines. I should have asked that before I showed you this. And I was asking it, and then you guys started asking better questions. So I put my question on hold, and then I forgot. All right. So do these lines indicate a paraboloid?
No.
Why not?
Because we don't have z values.
Oh, I just didn't write them on there. They're all as constant z value. So they imply z values even if the numbers aren't there. Is that what you're getting at? That the numbers aren't there? Yeah, there's numbers that are just not included. So is it a paraboloid? Yeah.
I think it is, right? Early x, y, there's one z value, so
Okay. So you're saying if you were to cut a paraboloid, you would get an ellipse, or you'd get a ring. You'd get a ring. Okay. What about the fact that they start further apart and then they get closer together as you get away from the origin? Does that indicate a paraboloid?
No, it's like the opposite. The paraboloid starts small and bigger.
Well, what does this mean? It means for the same horizontal change, you're getting more and more vertical change, right? So over here, for small horizontal change, you don't get much vertical change. And then the further you get away, you get more and more vertical change away from the origin. Does that indicate a paraboloid?
Yeah.
Yeah, right? And then is it circular or elliptical?
It's elliptical.
Elliptical paraboloid. Okay, so I'm just showing the part of that elliptical paraboloid in the first octant. I just only showing the first octant, and then it would keep going down also. So just a section of that in the first octant. Okay, so there's the 0.22. Here's the 0.22 that I was showing you, and now here's that in this other representation of this function. Here it's 2,2 in the xy plane, and then actually on the surface. So like this is like. So let's call this function h. So this is the function h equals h of xy. 1/2 x squared. Sorry, negative 1/2 x squared minus 1/4 y squared plus 4. So what indicates that it's elliptical in the equation? How do we know it's elliptical from the equation? What is it that makes it elliptical from the equation that is not circular? Plus 4? These denominators, right? That they're different. Remember? X squared over radius squared, y squared over radius squared. So it's these different denominators. How do you know that it opens downward, right? How do you know that it opens downward from the equation? Both of these are negative.
What if just y was negative?
What's that?
What if just y?
It would be a hyperboloid, and we didn't learn those. Okay. Yeah, no, that's a good question. All right, so what we're looking at then is we're thinking about from that 0.22, we're thinking about, where's my circle? Circle, circle, circle. No. No. I updated this file. Where is it? It's up here. There it is. Okay. So we're thinking about from that 0.22. So do you see that that circle is exactly the same as that circle over there? Do you see that? They're both in the xy plane. Center is 2, 2. So you need to see when you look at this and you look at this, that circle is really, those circles are really the same. Because that's the xy plane. The blue lines are showing z values. You're looking at the xy plane, and the blue lines are showing, the blue curves are showing z values on the yellow surface. Okay, and so then we started talking about this direction. This direction indicates what rate of change? What rate of change is this direction? What do we call it? What do we call that rate of change? Partial derivative with respect to x, right? And then we also talked about, and there should be, I don't know where that goes when I get to there, but it should be, just disappears, yes. What about this? So that's where we've lived the last week. These two derivatives. If you let x change a little bit, what's the rate of change of z? If you let y change a little bit, what's the rate of change of y? That's the partial derivatives. But now what we're saying is we can take changes of x and y in combination, and by taking them in combination in different proportions, we can get the rate of change in any direction. So what was the one we started with? -4 in x to 1 in y, so maybe something like that. So that was the one that we just worked out. Our unit vector was? Right. Right, so if you take so we saw that if you take the dot product of the vector partial derivatives and then the unit vector for that direction, which was -4 over radical 17, comma 1 over radical 17, that dot product would give us the rate of change in that direction. Okay, so And would we expect, let's see now. So there's another, so that unit vector indicates direction, but there's another way to indicate direction. What's one quantity that will give us direction, any direction around a circle? What's one quantity that could pinpoint a direction around the circle? Angle measure, right? So an angle measure, a single angle measure, is another way to determine, to get that unit vector for direction. So right now I'm showing, I mean to show pi over 3. So that's a little bit bigger than 1. There you go. So this is theta equals pi over 3. So this is the standard trig angle, right? The standard trig angle is swept counterclockwise from the positive x-axis. It's the same trig angle you've dealt with your whole trig career. So I guess I erased the function somewhere there. No, I don't have a... What did I do? There it is. Come back. There we go. So if the function is negative 1/2 x squared minus 1/4 y squared plus, what did I say? 4. I want you to find, and what would we expect? Would we expect the rate of change at theta equals pi over 3 here at 2, 2 to be positive, negative, or 0? Let me help you out. No, wrong plane. This one. So now that plane cuts through at the angle pi over 3. So in this direction, do you expect the rate of change to be positive, negative, or 0? So we got to understand what we're looking at here. So this is the direction of pi over 3. So here's that point on the surface. So if you were on the side of a hill, right there, and you were to take a step in the direction of pi over 3, which is this way, this red vector here, what would z do? Down, right? That's what this trace is showing on the blue plane. That's showing that z goes down when you walk in that direction. So we're expecting a negative rate of change. So I want you to find the exact value of the rate of change. What's the exact value of the rate of change? If you go in the direction of theta equals pi over 3 from this point. Remember that? The directional derivative, in this case is h, right? It's function h, not f, is gradient of h dot unit vector in the direction you want. See if you can do it. What's the rate of change of this function in the direction of theta equals pi over 3?
If you want
That's
to,
it.
it's
Pretty
much. Pretty much.
Which is what
Pretty much. Like going to look at the clock.
So if I have the angle, how can I generically write the unit vector for an angle theta? What is the unit vector for an angle theta? Caden. X coordinate given the angle is? So on the unit circle, what's the x coordinate of the point if you swept an angle theta? No, any angle theta. How did you, x coordinate? So the way we started with this direction was I gave you a proportion. I gave you a proportion of changes of x and y, right? And we found the unit vector for that proportion of changes, which is valid. But another way to specify a direction is by theta. And then so to get your x and y coordinates on a unit circle or for a unit vector, that's exactly what cosine and sine are, right? Cosine is the x coordinate on the unit circle. Sine is the y coordinate on the unit circle. And if you didn't remember that today, today's the day. You'll never forget it. This is the most important kind of basic thing about trig. On a unit circle, the x-coordinate given an angle theta is cosine of theta. That's the definition of cosine. The x-coordinate on the unit circle given an angle theta. And then sine theta, the y-coordinate of the point. So this would be a generic, that'd be a generic. So now what? Now we need the partial at, so what was our partial with respect to x?
Negative x.
Negative x, partial with respect to y?
Negative 1/2 y.
Negative 1/2 y. And what's our angle?
5/3.
Everyone following? So we've got -2, -1, and we said the rate of change should be what? Positive or negative? Going in this direction, you're on the hill. This is like you're on the side of a hill. You take a step in this direction. You're going up or down? Down. Z goes down. So we're expecting a negative value. Cosine of 1/3 is? Sorry, pi over third? 1/2. Sine of pi over 3? Okay, someone said wait. Did I lose you? We're at the point 2, 2, right? So this is our partial derivatives, but we're particularly at the point x equals 2, y equals 2. So I'm plugging those in here. If I'm at a different point, then I have different values according to this functions for the partial derivatives. So this is -1 minus radical 3 over 2. Did I do the math right?
Is it, sorry, we're
Please.
getting mixed up with trig. So
Please.
cosine pi over 3 is 1/2.
Uh-huh.
Cosine pi over 3 is 3 over
That's right.
Okay, we've said it.
Yep, that's right. Other clarifications, questions? We good? All right, so what kind of value is this? But what kind of quantity is it? Is it temperature, distance, velocity, acceleration? Why did we do all this? To find what?
That's a great question.
David?
So I just have a question about did you not utilize it because it was already in the circle?
Yeah, the definition of cosine and sine are coordinates on the unit circle, meaning radius 1. Yeah, that's the definition of cosine and sine. But if you do the magnitude of this, it'll be 1. Yeah, any cosine and sine you take together, take the magnitude, you'll get 1 because those are coordinates on the unit circle. Okay, what kind of quantity is this? What did we just calculate? Please, somebody know this.
Something in the direction of.
Yeah, something in the direction of you. What does that give you?
It's the directional.
Yeah, what does that give you? What kind of quantity does that give you? Derivative.
Rate of change.
Rate of change. In the direction of you. Okay? So, what does that mean? What does that mean? If that's a rate of change, what does it mean?
It's the rate.
Okay, you're right. It's the rate of change. What is Tyler? Right, and then so therefore, what does that number mean? What does that? How do you interpret that number? If it's the rate of change at 2, 2 in that direction.
At 2, 2, so that goes down by 1, whatever.
Yeah. Anybody?
Yeah, at that point, Z's slope is decreasing.
It's not that the slope is decreasing. Z is decreasing, so slope is negative. Can we apply what we've been learning about partial derivatives? This is
Given like a small change.
Brandon, save us. Listen.
It's bold.
Go.
I'd say like given a small change in x and y, or right, yeah, the resulting change in the z would be that times the change in x and y.
Yeah, in that direction. So given any change now in that direction, given any combination of dx and dy, hold on a second. Given any change in that direction, meaning in that proportion of changes of x and y, the resulting change in z would be that number times whatever change you picked in that direction. It's the rate of change, so it's the same thing as before. It's just now everything, the initial change that you pick has to be in the direction of pi over 3. Then how much z changes will be this number times as much as the change that you pick in that direction. Yeah, please.
Okay, so just for like my concept, so you just find that change in that specific vector instead of like your x and y vectors. Am I getting that right?
So a change in this direction means changes of x and y taken together that maintain this proportion.
Okay.
So that y is always radical 3 times as much as x. So you're walking along, you're walking in this direction, which means whatever your change in x is, your change in y has to be radical 3 times as much as that, and then you'll maintain this direction. Then whatever distance you go in that direction, your change in z will be that number times the distance that you go along the blue vector. Okay.
I'm thinking of like a hill, and like you're walking down the hill, and you're just seeing like.
Yeah. So here's the tricky thing about this. When we talk about direction, that's horizontal. That's an R2 phenomenon. The unit vector is an xy vector only. So you're staying horizontal. All right, so this is the key thing. The direction of this blue direction or this unit vector is horizontal, right? So it's like, which direction do I choose to go? Horizontally, x, y, R2 phenomenon. Then once I've chosen that direction, I'm calculating what rate of change. The rate of change of up or down versus going in that horizontal direction. It's a change in z per change in going that direction. Does that make sense? So the direction, your unit vector, R2. It's just an x and y vector, horizontal. Then once you calculate the rate of change, that's z per going in that direction. So up and down. Okay, I think so too. All right, so let me turn off the wood. So then if I were to go, take a look. So imagine you're standing on the side of the hill. So like this one right here. So our negative, the first one we did, which was something like that. Ratio of change in x to change in y was -4 to +1. What would you expect for the directional derivative? Negative, positive, or 0? I'm showing it here. I'm showing that first example we did. Why positive?
In random directions, so that changes.
What's the rate of change right here?
You see what I'm saying? You see what I'm saying?
Positive, negative, or 0? Positive, because if you go in that direction, this is this direction that we started with at -4 to 1. What happens to z? Z increases, right? Z goes up, right there. Okay, so as we turn all directions here, there's some kind of special rates of change. What would be special about all these rates of change? Which one we might be interested in? So this is fourth quadrant rates here, third quadrant rates, second quadrant rates of change, first quadrant. What's that?
Start to sort of become the same.
When there isn't a change.
Okay, good. So Cutter says it's right about. I'm trying. What about this direction?
There's no change.
Yeah, if you're staying on the side of the mountain, and it's a continuous smooth mountain like this, there has to be some direction where if you took a step, what would happen? 0 rate of change, right? You'd stay at the same z level. And there's actually 2 directions. Where would the other direction be? Exactly opposite of that, right? Now look at the contour lines. How does that direction compare to the contour lines? Yeah, just that first little step, you'll stay on a contour line. Why does that make sense for 0 rate of change? Z doesn't change, right? If you walk along a contour line, take a step on the contour line, Z doesn't change. So that would be the direction of rate of change is 0. Okay? So we'll get back to that one, but there's something else here. What about through here? There's a special rate of change right through here. Well, local, it's always locally linear because it's right at the point, right? So it's always kind of locally linear. So somewhere here, there's a. And what are you thinking, Colin?
Pointing directly towards the center is the maximum.
All right. What about maximum rate of change? So what's happening to the rate of change here? Is it increasing? And then back over here, it's decreasing. So somewhere in here, there is maximum. Let's figure out where that is. Here we go. Let's figure out where the maximum rate of change is.
Mine is like 145.
All right. This is review. The derivative in the direction of theta is the vector of partial derivatives times the unit vector, right? And we said this. Our function was h, so it'll be the gradient of h dot u. So remember with dot product, there's 2 ways to compute the dot product. What was the other way to compute the dot product besides multiplying components and adding? Do you remember? Remember what the other way of computing the dot product was?
It's rewind time.
We're on the right track.
So that other way of calculating the dot product was reflective of our meaning for dot product, which was?
Was that the work example that we did?
Okay, that had to do with it, yep.
It's like magnitude.
Product of the magnitudes, what?
Times cosine theta.
In as much as they're in the same direction. So what was that formula? Product of the magnitudes, cosine. Now, what was the angle? We did that. That was the angle what? Between the vectors tail to tail, right? Is that the same as theta? What is the angle theta?
From x to.
Yeah, to u, right? So theta is using the standard trig angle to give us our direction of u. This angle, I'm calling it something different because it is something different. It's the what? Angle between these 2 vectors, which is between u and the gradient vector. So it's not theta because it's not theta. It's the angle between these 2 vectors. Now, what's the magnitude of the unit vector? Therefore, I can simplify this as just the magnitude of the gradient times cosine alpha. What is that again? That's another way to calculate directional derivative, or the rate of change in the direction of u. Magnitude of the gradient times cosine, where this angle is the angle between the unit vector and the gradient vector. And what were we talking about? We wanted to ask about when is this maximized? So what's the biggest that can be if it's something times cosine alpha?
That's 1.
The cosine, and what alpha is? Right, right. So the maximum value of the directional derivative is when cosine alpha equals 1, because that's the biggest cosine alpha can be. And so then the biggest value of the directional derivative is the magnitude of the gradient. That's the biggest it can get. So what direction, so then the alpha tells us the direction we need to choose to get that maximum rate of change. So how do we get cosine alpha to be 1? Giorgio said? Alpha equals 0. And what was alpha again? Angle between these vectors. So how do we pick the unit vector so that the angle between them is 0? It's easier than that. No. So, no, I need the, what does it mean for the angle between two vectors to be 0? The same direction, right? So I'm going to pick u. U is what I get to pick. I'm going to pick u to be in the direction of parallel to that. And then the angle between them is 0. Did you catch it?
Yeah.
I need alpha to be 0. Alpha is the angle between these two. So the angle between those two being 0 means they're pointing in the same direction, which means I choose u to be in the same direction as the gradient. So I want to make u the direction of the gradient vector, and then that will give me the direction of maximum rate of change. And then I'm going to take the magnitude of the gradient, and that's going to give me the biggest rate of change in that direction. So for the example I gave you, I want you to find the direction and magnitude of greatest rate of change for the paraboloid that we were looking at on the previous slide. What was the gradient at 2, 2? Negative 2, remember? Negative 2, negative 1. That was the gradient vector at our point. So, what's the maximum value of the directional derivative at 2, 2?
Is the magnitude of that?
The magnitude of that, that's what we found. But the maximum value of the directional derivative is the magnitude of the gradient. Therefore, for us, 5. Square root of 5. Square root of 5, right? So the magnitude of our h at 2, 2 is square root of 5. And then which quadrant will we point, or which direction will we go to get that maximum rate of change? It's going to be, we want to make u in the direction of the gradient. So what's the direction of the gradient? Yeah, Brandon.
How did you find the square root of 5?
The magnitude of the gradient vector.
Oh, okay.
You see that?
Yeah.
Yeah, it's going to be magnitude of that. Direction is? It's just that. So you can just write that, or you can write the unit vector. Direction doesn't matter what the magnitude is. So if you want to make unit vector, it's fine, or you can just say the direction is going to be in the direction negative 2, negative 1. What quadrant does that point in? Third. That's what we saw, right? So let's see it for real here. Okay, where did I lose you? Please ask. Yeah. Because we showed here that the directional derivative is the magnitude times cosine alpha, and we want that as big as it can be. That's as big as it can be when cosine alpha is 1. So the biggest the directional derivative can be is the magnitude of the gradient. So I found the magnitude of the gradient. Better?
Yeah.
Okay, cool. All right, let's see it. Here we go. All right, so that vector is right here. Okay, so yeah, if you need to take off, go ahead and take off quietly, but can we just take a couple minutes to see this? So there's right there, that's the direction of negative 2, negative 1. Slip out quietly so you're not blocking other people's view of the screen also. Thank you. So there's -2, -1. And what do we notice? If you look, if you go in that direction, what do you see? Heading up at the steepest, this is the steepest ascent of z that you'll head going in that direction. And what is that rate of change? Square root of 5. That's the biggest rate of change you'll get, and that's in the direction of the gradient.